Morning, class. Um, Sorry I'm a little bit late. I lost track of time there during the passing period. All right, I'm at 20 people, so I think I'm going to start. So, good morning, everyone. This is my first class of the day, so I have to get my camera set up. So today, we are going to start a new topic, which is called waves. So we are talking about waves. And this is not unrelated to simple harmonic motion. So what I want to think about is imagine that you are in the ocean, okay? And so you have a water wave that looks like this, okay? And so here's the water wave, and it's so this is a traveling wave over the surface of water, okay? And so this is just a picture of it, and you are swimming in the ocean. So you are right here floating, and so this is you, and then here is your friend who is also in the ocean floating. You're both swimming together, okay? So this is your friend. And so what I want to think about is this wave as it passes by. So this wave is actually moving. So later on it's going to be, over here like that. It's moving as waves in the ocean do. And so what I would like to do is I would like to go ahead and draw a position, an elevation as a function of time graph for u, okay? And so what you will find is as this wave passes you by, it's going to lift you up, and then it's going to lower you down, and it's going to lift you up, and then it's going to lower you down, and it's going to lift you up, and it's going to lower you down, just like when you're in a boat, okay? So if we were to look at the y versus time for you, it's going to look like simple harmonic motion, okay? And you can see that you start off high, so it's going to look like this, something like that. So this is your position time graph. But then now let's think about your friend, okay? Your friend is at a different location, okay? And so basically, because of the spacing between the two of you, whenever you are up high, your friend is down low. And then once the wave lowers you down, your friend is going to be up high. So your friend's position time graph is going to look like the opposite of yours. So it's going to be like, something like this. So this is your friend's position time graph. Okay. So basically what I'm trying to say is that wave motion is really, really closely related to simple harmonic motion. Okay. You are undergoing simple harmonic motion, and your friend is undergoing simple harmonic motion, but those simple harmonic motions are out of sync because you're at different locations. Okay. So let me define a term called the medium. So the medium is the thing a wave travels through. The thing a wave travels through. So in this case, because it is a traveling wave over the surface of water, the surface of the water is the medium. Okay? And so we could think about a wave is a disturbance that passes through a medium that causes different parts of the medium to undergo simple harmonic motion. Okay, so every single point in the medium, if we looked at the position time graph of that spot on the medium, it is also going to be undergoing simple harmonic motion. But all the simple harmonic motions are out of sync. So that is why I always teach simple harmonic motion before waves, because in order to understand how a wave works, you have to understand simple harmonic motion. Waves carry energy from place to place. Okay. So now let's think about it. There are some different properties describing a wave. Okay. So if we look at the crest of this wave, maybe at time 1, the wave looks like this. Because this wave is traveling at a later time, the wave is going to have moved a little bit. So now it's going to look like this. Okay? So this is at time 2. And then at time 3, it's going to move even further. So the wave is moving as time goes on. And what we could imagine doing is we could imagine tracking the peak of the wave. Okay? We could talk about the position of the peak of the wave as a function of time. And so that is going to be the rate at which the peak of the wave is moving is called the wave speed. Okay? So there is such a thing as the wave speed. all right, which is basically the speed of the peak of the wave. And an important point about the wave speed is that it depends on the medium and on, so it depends on the medium. So whatever the medium is, that is what is going to determine the speed of the wave. So for example, the speed of sound through air is about 340 meters per second. And I can't give you an exact number because it depends on the conditions of the air. So as the air changes its temperature, as its humidity changes, those things change the properties of the medium, which causes the air to travel at a different speed. But just in typical conditions for the Earth's atmosphere, it's about 340 meters per second. The speed of sound in water is actually much higher. It is about 1,500 meters per second. Okay. And the reason for that is that water is, you can compress air, but water is a lot more difficult to compress, and for that reason it doesn't like waves passing through it. So when a wave travels, it's almost like playing hot potato. If you've ever played hot potato, it's like you get the potato and it's really hot, so you pass it to someone else really fast. That's kind of how sound waves travel through a medium. It's part of the medium gets compressed, and then the medium doesn't like that because it puts stress on the medium. So the medium then passes it on to the next location. And so water really doesn't like to be compressed, so it passes on that compression to the next location really quickly. Okay. So actually, the stiffer the medium is, the faster waves will travel through it usually. So if we think about the speed of sound in through metal or earth or anything like that, those are even more stiff than water. So it's going to be 2,000 meters per second plus, and that depends on the properties of the earth. So I can't give you a specific number. Okay, so that's called the wave speed. It's determined by the properties of the medium. Different waves have different speeds, so different types of waves have different speeds. So a wave traveling over the surface of water is completely different in terms of its mechanics than a sound wave, so they travel at different speeds. Okay. All right, so if we look at waves, we can do two graphs for waves. One graph we can do is a displacement of a single part of the medium versus time. So displacement of a single part of the medium versus time. So that is like these graphs, okay? So it's going to look like simple harmonic motion. So you have displacement of a single part of the medium versus time. Simple harmonic motion, okay, you can define the period, which is the time it takes for one vibration to complete. So that is called the period. And then we can also define the amplitude, okay, which is how far the wave deviates from its center line. All right, so that is exactly the same as simple harmonic motion. Now, there's a thing called the frequency, which is denoted by F, and the frequency is equal to 1 over the period. All right, and what that is the number of wave oscillations per second. All right, so how many times does the wave cause you to go up and down per second? That's the frequency. The units of frequency are called hertz. All right. So 1 hertz would correspond to 1 vibration per second. So it's kind of like 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000. A frequency of 3 hertz would be 3 vibrations per second. 1, 2, 3, 4, something like that. A frequency of 5 hertz would be 5 vibrations per second. So 1, 2, 3, 4, something like that. All right. So frequency is how often is the wave lifting you up and down. Okay. There's a second graph that we can draw for waves. All right. So, and this one is displacement versus position in the medium. Okay, so this graph is going to look literally like a photograph of the wave. Okay, you know, if you're watching a wave from above the water and looking at what does it look like. So this is a displacement versus position, because these different spots are representing different points within the medium, different locations within the medium, and then we have the displacement of that particular point. So it is going to look like also like a simple harmonic motion graph, but it has a completely different interpretation. So this graph might look like so. Like that. Now, if we look at how far, what is the maximum displacement from equilibrium? That is the amplitude. Okay. If we look at how much space is there between peaks, okay, that is called the wavelength, which is denoted by the Greek letter lambda. Okay, so the wavelength lambda is equal to the space or the distance between peaks. All right, so the period is the time between peaks. The wavelength is the space between peaks. Okay, we can't get the wavelength from this graph because this only has displacement versus time. So if it's displacement versus time, you can get the period from that graph. If it's displacement versus position, you can only get the wavelength from that graph. From either of the two graphs, you can get the amplitude, because the amplitude is just how far from what is the maximum displacement. Okay? So, let me write that down. You can get the period from a displacement time graph. All right. And you can get the wavelength, which is the Greek letter lambda, from the displacement versus position graph. You can get the amplitude from either graph. All right, so that is useful. So it turns out that the velocity, the wavelength, and the frequency are related to each other. All right. The velocity, the wavelength, and the frequency are related to each other, and there's a nice equation that relates the three of them. It is V equals lambda F. You might have seen this equation in chemistry with regards to light waves. In chemistry, you might have seen it as C equals like lambda nu, because C is the speed of light waves, and chemistry sometimes uses the Greek letter nu for frequency. Type it in the chat if you've seen that before. It's the exact same equation. So let's go ahead and do an example. So I'm going to draw some waves. So I have displacement in meters versus position in meters. And this graph is going to look like this. Three, 4, 5, 6, 7, 8, 9. 3, 4. Okay. So that's the displacement versus position of the wave. And then next to that, I will draw the displacement versus time of the wave. So we have time in seconds, displacement in meters, and this one looks like so. Let's say like that. 5, 6, 8, 9, 10, 13. 3. Okay, so we have these two graphs, and now let's go ahead and figure out some different things about this wave. So first of all, what is the amplitude? Well, the amplitude is the distance from the center line of the wave to the peak. And I can use either graph to do that. So that is going to be this distance right here, which looks like it's about 3 meters. Okay? And notice how I could use either graph, because if I use this graph, I also get 3 meters. Okay? You can use either graph to do that. So the amplitude is 3 meters. Now we can go ahead and get the period of the wave. So the period, you can get the period from the displacement time graph. So this is displacement position, so I don't use this graph, I use this one. And so the time to complete a full vibration would be this amount of time. And I drew that as 11, 12, 13. About 13 seconds is the period. Now, from the period, we can get the frequency. The frequency is 1 over the period, so that's going to be 1 over 13. Which is 0.077 hertz. So that is the frequency. The next, well, let me box these in. The next natural thing to calculate is the wavelength. And the wavelength is the space between peaks. So I can calculate the wavelength as the space for a full vibration. So down, up, down, and back to center. And so I can see that that took about 6 meters of space. So there's 6 meters. Alternatively, I could look at this peak is about 1.5, and this peak is at about 7.5. So that means that the wavelength is about 6 meters. Now, once I have the frequency and the wavelength, I could calculate the wave speed. So V equals lambda f. So we have 6 times 0.077 and that is 0.46 meters per second is going to be the wave speed. It's a pretty slow moving wave. All right, really slow moving wave. So that's a basic problem. Some other problems you might see are just playing around with this using V equals lambda f to solve for lambda, or to now the thing you want to remember is that the wave speed is determined by the medium. Okay. The frequency is usually determined by the source of the wave. So if I'm making a water wave, the frequency is going to be determined by how often I push down on the water. Okay, if I'm making, all right. If you are playing a musical instrument, the frequency is determined by the note you choose to play. So it's the frequency of the sound wave is determined by the source, which is the instrument itself. The medium would determine the wave speed. So the wave is going to, because it's traveling through air, it's going to go at 340 meters per second. The frequency is set by the instrument and how quickly the string is vibrating. So then the wavelength is usually calculated from this equation. Let's do another example. Let's say that there is a you are standing in front of a wall. Actually, no, let's say that you're in the ocean. Okay. You're floating in the ocean, and as you know, you can actually yell underwater and you can hear it. So you can make a sound wave. All right. So you yell, and the water, let's say that the water is 50 meters deep. So you're like in the ocean. Okay. You're not close to the shore. And you yell with a frequency, so you produce a sound wave with a frequency of 800 hertz. Okay? So my first question is, what is the wavelength of this sound? Well, if we take the equation V equals lambda F, and we divide both sides by F, we get that lambda is the wave speed divided by the frequency. This is a sound wave that is traveling through water. So the speed is going to be 1500 meters per second. And then the frequency is determined by the source, which is U. Okay, so 800 hertz. And so calculating, doing the division, 1500 divided by 800 gives about 1.9 meters as the wavelength. So that's one thing we can calculate. We can also calculate what is the time for the, hopefully you guys know what an echo is. So what an echo is when a wave goes out, it hits the surface, and then it bounces back. Okay, so that's an echo. So what is the time for the echo to return? Well, waves travel at a constant speed through us. If you just have a consistent medium, the wave is going to travel at a constant speed. It is possible for waves to jump between mediums. Okay, like if you were to shine a light through the air, it can enter the water. So waves can change mediums, can jump between mediums, and when they do that, their speed will change. But if you have a single medium, then the wave is just going to travel at a constant speed within that medium. So we have speed equals distance over time. All right. Now, because it is a water wave, a sound wave traveling through water, we know that it is going to have a speed of 1500 meters per second. And now here's the thing about echoes. The wave does not travel 50 meters. It actually travels 100 meters because the wave has to go down and it has to bounce back. So it has to travel this distance 2 times. So the distance it travels is 100 meters. Divided by the time elapsed. we can solve for the time for the echo to return, which is going to be 100 over 1500, 0.07 seconds. So it returns very quickly. So one last thing I wanted to talk about before we go to the Zoom room, and that is that our ears are sound wave detectors. Okay, and our eyes are light wave detectors. Okay, so 2 of our 5 senses are detectors of waves. Okay, now how does our brain process the properties of a sound wave? Well, for a sound wave, it turns out that frequency our brains perceive as pitch. So is it a high note or a low note? La, la. Those are changing the frequency of the sound wave. Okay? So frequency is pitch, and then the amplitude of a sound wave is volume. Okay? So a big amplitude sound wave we would perceive it as being very loud. So volume / loudness. For light waves, we perceive the frequency of the light wave as its color. All right? And we perceive the amplitude of a light wave as its brightness. So our eyes are light wave detectors, our ears are sound wave detectors, and then our brain processes that and interprets it, and the way our brain interprets frequency and amplitude, are basically our 2 pitch and volume, and then color and brightness, which I think is kind of interesting. Now, 2 of our other senses, smell and taste, are basically they're not detecting waves, they're actually detecting chemicals. So our senses are kind of either wave detectors or chemical detectors. When we taste something, we're basically detecting chemicals in a liquid. And when we smell something, we're basically detecting chemicals in a gas. And then the sense of touch is more of a pressure sensor. So it's when your body gets pressed on, it sends an electrical impulse to your brain. So, anyways, my point there was that your senses can be broken down into physics concepts. All right, so that is my lesson for today, and I will see you in the Zoom room. Bye-bye.